All right, so we've previously touched a little bit on curve sketching in a different section. And so now I'm going to go a little bit more in detail with these. I want it to be its own section here. All right, so this first part says complete the table by sketching the general shape of the curve when each condition is met. So we have the first and second derivatives. So it depends on what, it's telling us. So if the first derivative is positive, that tells us that f is increasing. And if it's negative, that tells us that f is decreasing. I guess I should say f of x. But the original function is increasing and decreasing. And then the second derivative talks about the concavity, right? So this means our original function is, the second derivative is positive, then the original function is concave up. And if the second derivative is negative, then the original function is concave down. So let's see if we can draw that. So what does a function look like if it's concave up and increasing? So I always think of parabolas, right? Whether we have an upward or a downward one, because I think all four pieces are within those two. So if we're concave up and increasing, well, here's concave up, and then the increasing part's that right side. So we could look something like this. I'm going to make it look a little better. But what about being concave up and decreasing? That's going to be that left side, right? And now concave down and increasing will be the left side. And concave down and decreasing will be that right side over here. Okay, so something like that, right? It's just the easiest for me to look at. Okay, so we might be given a whole bunch of different conditions, and we want to try and draw a function that meets those conditions. Now, the one that I draw is not going to be like the end-all be-all. There are many other ways we could draw things that are going to meet these conditions, but I'm going to do it at the most basic level. You can get fancy with it if you want, but just based off of these, I'm going to draw a basic one. So we have a function whose derivative is positive. Sometimes with these, I like to also draw out what's happening because we're working a little backwards. We usually are given the original function, and then we find the derivatives to find out what's happening with the function. And this time we're like already given what's happened. And so I like to draw out some things. So if I do my sign chart here, let's see, we're positive from negative infinity to negative 1. So that means we're increasing. And from 3 to infinity. But then we're negative from negative 1 to 3. Okay. Now we have the second derivative. From negative infinity to negative 3 and negative 1 to 3, we are positive. And then negative elsewhere. Okay. And then the limit as x goes to negative infinity for the function is negative 4. But as we go to positive infinity, the limit is positive 4. All right, so I'm going to try and draw g of x here. So as we go to infinity, right, this direction, we're reaching 4. 1, 2, 3, 4. So eventually, at some point, we are reaching here. Maybe I'll even kind of draw that. And as we go to negative infinity, we're going to negative 4. So eventually, we'll be going that way. We have different points here, right? We have a maximum negative 1. We have a minimum at 3. And then we have changing in concavities at negative 3 and negative 1 and positive 3. All right. What else does it give? That might be it. All right, so we are positive. First derivative is positive. So it means the original function is increasing from negative infinity to -1. And at -1, we have a maximum. So why not pick a point? Doesn't give us any other information. So, all right, we're increasing. I'm going to turn to decreasing because this tells me I'm decreasing, and because that told me it's a maximum. And and I might fix something. So let's not, if you're following along, let's not draw it until I am completely done. So, all right, at 3, we have a minimum. So, all right, and we are decreasing. And then we eventually turn back to increasing and we have a minimum. And then we eventually want to get back up there. So let's just connect it and see what happens. So let me make sure I have met all of my conditions. So I've met the increasing part. Now I'm going to check the concavity. So from negative infinity to -3, I am concave up. I believe that looks pretty concave up, right? Then from -3 to -1, we are concave down. And then from -1 to 3, we are concave up. This says concave down the way I drew it. So let's change that. Just that one section here. And maybe I can change that as well. Concave up. Alright, so concave up. Oh, I can put that minimum back here. I can just make it, instead of like a smooth transition like I was doing like that, it can be like a cusp situation here. So concave up and then back up. So let's double check that again. So we got that first part, concave up, concave down, and then we switch to concave up, and then all the way to 3, and then we're back to concave down from 3 to infinity. So maybe make that a little bit more pronounced here. Concave down like that, and I can get rid of that. Now I think it meets all the conditions. And now you can draw. So that's why I say don't draw it until it's completely done, just in case we have to fix something, right? All right. We've got this graph. Suppose the graph shown above is the original function. So on what intervals are we increasing and concave up? So I'm decreasing, I'm increasing, oh, and then concave up. So from -5 to -2, and then we're concave down, down. This is up, but we're not increasing. And all right, so 4 to 6, and then increasing, but then concave down. All right, on what intervals are we decreasing and concave down? So that is going to be from -2 to -1, right here. And then, oh my gosh, that's increasing and concave down. That's crazy. This is decreasing and concave down. So -1 to 2. And then that's concave up, that's concave down, but increasing. So just that one section there. What x values do we have inflection points? So that's where we're changing concavity. So concave up, and then we switch. So at -2. And then we're concave down, and then we switch to up. So then 2, and then up, and then we're back to down. So at 6 as well. All right. Well, now let's look at that same picture, and we're going to look at it as if it's the derivative. All right. So on what intervals is the original function decreasing? Well, that's when the derivative is negative. So that's going to be from 2 to 6. And what x values do we have a local maximum? So that's when the first derivative is set equal to 0. And the maximum is when we're changing from increasing to decreasing, or changing from positive to negative. So if I look here, there's no sign change because both sides are positive. But if I look here, I'm changing from positive to negative. And if I look here, I'm changing from negative to positive. So I'm only really looking at that x equals 2. All right. On what intervals is the function concave down? Well, that's when the second derivative is negative, right? Or it's when the first derivative is decreasing. Or the slopes are negative. So that's going to happen right here from -8 to -5. And then, let's see, positive slopes, and then negative, so -1, and that's negative slopes all the way to 4, so -1 to 4, and that might be, yeah, the rest are positive slopes. All right, at what x values does the original have an inflection point? Because we are looking for when we'd want to look at when the second derivative is equal to 0, which in this case we have the first derivative, right? So we want, where would the slopes be 0? And so we're looking at here, here, and here. So that would be x equals -5, -1, and 4, right? All right, now we're going to look at the graph as if it's the second derivative. So, on what intervals is the original function concave down? Well, that's when the second derivative is negative. So, on this graph, we're negative from 2 to 6. And then what x values does the original function have inflection points? Well, that, again, is when the second derivative is equal to 0. So, in this case, we're going to have equal to 0 and changes sign. So that's equal to 0, but we don't change sign. So 2 and 6. 2 and 6. All right. So that's all for that. All right, so the actual, start to finish, how can we just analyze a function if we're just given the function itself, right? Here's some guidelines for you. So we can, if we're given just the function in general, we can find the domain, probably any x and y intercepts, if there's any asymptotes, and if we remember our symmetry rules, we might be able to find the symmetry. And we might be able to get a general shape of the graph depending on what kind of function it is, or at least have an idea of what it could look like. And then after we've done the basics, we can go further and find any critical points so that we can find exactly where the function is increasing and decreasing and where there's any maximums and minimums, right? That's that next step. Determine the local maximum and minimum points. And then we can do a second derivative and find the concavities and points of inflection. And then we should have enough information to be able to draw a graph. So let's look at this function. G of x is x plus 2 times x minus 1 quantity squared. So if I were to multiply all of that out, that's going to give me some kind of x cubed function. And we know, based off of the power and the leading coefficient, that we will look something like this, right? There's potential for us to look like that. Because at most, we'll have 2 turning points, right? The degree minus 1 is the most turning points that you will have. Yeah, we'll go from there. So find any x and y intercepts. So the x-intercepts, we are already factored completely. So the x-intercepts come from that. So -2, 0, and 1, 0. And if we remember our multiplicities, right, this would be an odd multiplicity, and this would be an even multiplicity. So what does that tell us? Odd tells us we cross the axis. Even tells us we touch the axis. Okay. And then the y-intercept, that's when x is 0. So let's plug that in. 0 plus 2 times 0 minus 1 squared. So that's going to give me 2. And then -1 squared is 1, which is going to give me 2. So the y-intercept is 0, 2. And did I give space to actually draw a graph? Yes. So let me go ahead and draw that, right? So we have a y-intercept of 0, 2. I have an x-intercept of -2. And it crosses, so I'm going to do some potential here. And then we have one at 1, and it touches, so I'm going to do potential right there, right? Because we know with that x cubed, we're going to look something like that-ish, right? So I'm just drawing my potentials. I find the first and second derivative. Okay, so I don't have to do product rule. I'm going to go ahead and multiply that out. So g of x is x plus 2 times, and if I multiply that out, I'm going to get x squared minus 2x plus 1. And now I'll have to multiply that out even further. So x cubed minus 2x squared plus x, and distribute the 2, so plus 2x squared minus 4x plus 2. So we have x cubed. Let's see, those will cancel out, and then I'm left with minus 3x plus 2. So now I can do my first and second derivative. So my first derivative is going to be 3x squared minus 3. And my second derivative will be 6x. So let's make those sign charts. So let's do the first derivative first. So that is 3x squared. Oh, I'm going to move that over actually. (3x squared minus 3). I can factor out a 3 and be left with x squared minus 1, right? And then that's a difference of squares, so I can say x plus 1, x minus 1. So then my critical points for this are going to be -1 and +1. And then I will use that to do some values. So here's what I do. I'm going to plug in 0, because that's between one of my intervals, right? So that's going to be 3 times 1 times -1. So it's going to be -3, so that's negative, which means we're decreasing, right? And then these multiplicities here are odd, so we're going to cross, right? So we are, there's my increasing and decreasing, right? Now let's do the second derivative. So that second derivative is 6x, which means that critical value is just 0. So if I plug in positive, I'll be positive over here, which means I'll be concave up on the original, and then negative over here, right? And concave down on that interval. All right, determine any relative extrema. So we do have some sign changes, right? So we have a maximum at x equals -1 and a minimum at x equals 1. And we do have the original function, right? I'm just going to rewrite it down here so I don't have to keep scrolling. So we have x plus 2 times x minus 1 squared. I can plug in these values so that I can have the exact points. So if I do -1, I get 1, and -1 minus 1 is -2, squared is 4. And then if I plug in +1, I'll probably get the same thing. Just kidding. Don't know why I said that. 1 plus 2 is 3. And then 1 minus 1 is 0. 3 times 0 is 0. Which this should not come as a surprise based off what I already have. So let's just go ahead and plug these in. So -1, 4, and 1, 0. -1, 4, and 1, 0. So I said that shouldn't be surprising at this point here because of my potential drawing already, right? It already made the minimum. So now we just verified that that's a little bit more accurate, right? And then we know this is a maximum, so I can do my, a little bit of potential here, right? And I can look at my increasing and decreasing later. Oh, I definitely have already done that up here. I'm just going to recopy it down here, all right? Whoops. All right. I should put this right here. Okay. So we got that covered. Find any inflection points. So we are changing sign right here at 0, right? So we'd have one at x equals 0. And again, I can plug that into the original, right? X plus 2, x minus 1 squared. So if I plug in 0, I already have done that, right? It was 0, 2. So it happens to be the same as the y-intercept. So I already have that drawn. And now let's put everything together. So we were increasing from -infinity to -1, which would make sense here with my potentials. Oops. Whoa. Right. Gosh, I'm terrible at drawing. That's awful. A little better. And then we're decreasing from -1 all the way to 1. And then we turn back and we're increasing. And then let's double check our concavities. So we're concave down from -infinity to 0, which looks like what I have. And then concave up from 0 to infinity, looks like what I have. And a flexion point at 0, 2, also looks like what I have here. And we did our maximums and minimums. So we are good there. All right, let's see if we can do one from scratch, right? So one that we have, I should have done a different function because this leading term is pretty much the same, right? It's an x cubed, but we have a negative x cubed. So it's going to look something like this, right? So that's not the best, but it's okay. Could have done a different function. So let's just go from the beginning. All right, so we want to find any intercepts is the first one. So the y-intercept to me is the easiest. So let's find that. So h of 0 is -2/3. So our y-intercept is 0, -2/3. And then x-intercepts. Ooh, these are fractions here. All right. Gotta think how I would want to do that. Yikes. Trying to think of my pre-calc knowledge here. We can do P and Q and find out what we have. So let's see. P is going to be that 2/3. Q is that 1/3. Okay, maybe I don't want to do that. I don't want to do that with fractions. All right, let's clear out the fraction. So let's multiply the whole thing. And I want to get rid of that negative because the x-intercepts will be the same no matter whether that leading term is positive or negative. So let's multiply this whole thing by -3. So I get x cubed minus x and then plus 2. And let's find it from there. P and Q will be easier there. So P is 2, Q is 1. So my factors are 1 and 2. And then my factors are just 1. So my P over Q for my potential ones are 1 and 2. So let's try and divide it out. So let's see. I can look at doing 1, 0, -1, 2, and let's just test 1. So 1, 1, 1, 0, 1 doesn't give me a 0, so that's not going to work. Let's try -1. So that's going to be -1. That's going to be 1. It's going to be 0. -1 also doesn't give me a 0. Oh my gosh, and you probably caught it before I did. This should be a -3, which means this should be a -3. So let's try again. So that's 1, 1, 1, -2, -2, 0. So actually, x equals 1 is a root. And then, let's see if we can go further. So that leaves me with x squared plus x minus 2. So could that be factored? X, let's see, 1 and 2. We want -2, +1. Alrighty, so it looks like we could factor that to be x plus 1, x minus 1. Sorry, x minus 1, x plus 2, and in the original we have a root of 1, so that's going to leave with x minus 1. So, alright, we have really 1 with a multiplicity of 2 and -2 with a multiplicity of 1. So we touch the axis here, but then we cross the axis here. And all right, this is all the space I gave myself. So I'm going to start my picture over here. So we have 0 and -2/3 as our intercept. And then we have a 0 at 1 where it just touches. And then we have a 0 at -2 where it crosses. And we know it looks potentially like this, so I'm going to kind of do some potential drawings just like that. All right, let's see what else. Let's do derivatives. So let's do the first derivative. Go back to the original function, so it's going to be -x² plus 1. So if I set that equal to 0 to find those critical points, I can add that over. So x² equals 1. So I get positive and -1. Just go ahead and do my sign chart here. All right, if I plug in 0, I get positive, and which means we'll crisscross. And then I can do my second derivative. Should be -2x. So if I plug in 0 to find my critical points, I get x equals 0. And if I plug in a positive number, I get negative, which means we'll crisscross here. And let's see, we got some minimums at -1. If I plug that into the function, let's see what that gives me. So negative 1 cubed is negative 1 times negative 1/3 is a positive 1/3. And then we have minus 1 and minus 2/3. So is that negative 4/3? 1/3 minus 3/3 is a negative 2/3 minus 2, so negative 4/3. So negative 1, negative 4/3 is a little over 1, which that tracks for my potential here, right? For a minimum. And then we have a maximum at 1. So I would have negative 1/3 plus 3/3 and minus 2/3, which, it being 1, we already have an x-intercept there, so I'm pretty sure it's going to be 0. But negative 1 plus 3 is 2. 2 minus 2 is 0. All right, so we knew that. And then let's see the rest. Decreasing until negative 1, increasing to 1, decreasing the rest. Concave up from negative infinity to 0, concave down from 0 to infinity, and that looks like that tracks my dotted line here. And it looks like it matches my original assumption based off that pre-calc knowledge of the leading term. And so there we have it. So that's just a little bit more on curve sketching. If you have any questions, let me know. And if there's any others that you'd like to see, let me know.